So one thing I've noticed is the book doesn't do a good derivative of e of x. It doesn't do a derivative of e of x at all. It just says, trust us, for f of x equals e to the x. The derivative is also e to the x. Well, that's okay. And then online, a lot of the derivatives are super confusing. And it turns out if you use implicit differentiation, it's a little easier to understand e to the x and even 2 to the x rather than using the incredibly confusing methods they use. They actually use, instead of 2 to the x, they use e to the ln of 2 to the x, and it makes it just pretty hard to understand where they're going or to memorize it. Now, I'd say for this one, the hardest one I'm going to show is that ln x, the derivative of this, is the same as 1 over x. Once you get to here, these things are actually easier using a thing called implicit differentiation, which is incredibly easy. Don't get scared by that name. The implicit differentiation is just saying we're going to take the derivative of y terms as well, as it relates to x, and it's very easy to do. So what I want to start with is an understanding of what is e. Well, e stems from a compound formula in terms of understanding. And e is just a magical number called 2.171, I think 58, I forget the other ones. It goes on forever. It doesn't repeat. And to get to e, you have to understand a basic principle, which is the compound interest formula. So if I give you $1, and at the end of the year, I'm going to give you 100% rate of interest in decimal form, which is 1. 100% is equal to 1. And I'm only going to compound it once, which is n. And I'm only going to use 1 year, so I can ignore the t, 1 year. So it's n here as well. So it's clear that I can ignore the dollar in front, because 1 times anything is just itself. But it's clear inside I have 1 plus 1 to the 1, which is 2. That makes perfect sense. You started with $1. I gave you 100% interest, and you ended up with $2 because I gave you 100% interest and only compounded it once. Makes sense. What if I compound it twice? I give you the dollar. You start with $1. I'm going to give you 100% interest rate, but I'm going to compound it twice, which gives me a 2 here and a 2 here. Well, this comes to 1.5 squared, which comes to more than $2, $2.25. Well, okay, it's clear that as we compound this more and more and more, we get more and more and more. And you can see that just by plugging in your calculator. Give it a try. Put 10 here and 10 there, so it's going to be 1.1 to the power of 10. And you're going to discover that number goes from 2 and climbs and climbs and climbs. And you think it's going to go all the way up, but it actually has a ceiling. That if I constantly put in giant numbers here, if I put in 1,000 here and 1,000 here, I hit a max. And that max is called E. 2.71 something, 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 something. And that E has a lot of interesting things about it that make it almost as interesting to mathematicians as pi. And so E is one of those numbers, but also keep in mind it's just a number, just as pi is just a number. Because you can get confused thinking, oh, do I have to derive that? No, it's just a number. It's a multiplier. So that's where E comes from. And if you graph E, if you graph this graph, y, I'm just going to try to undo it all here. Whoop. If you graph it, you're going to get y is equal to e to the x. Well, that's the same as y is equal to 2.71 to the x, and it's clear it's a growth curve. But what's interesting about this growth curve is whatever value I'm at on the y, so if I'm up here at 5 when x is 5, then y is e to the 5. But if I take the derivative using my instant rate of change formula, I'm going to discover the derivative is also e to the 5. So the derivative matches the y values. And that's why it's a fascinating graph. And we're going to get into that. But before we can derive it, I want you to understand one basic thing. And that's how to derive this one. The derivative of ln of x based on the changes of x is equal to 1 over x. But if we can get that, these other ones are going to be easier. So I want to focus on that. I also want to focus on something called implicit differentiation. But let's spend some time on 1 over x. And for it, we're going to have to remember the definition of e. So when I'm going to do the derivative of ln of x, I'm going to take the old-fashioned limit as h approaches 0 of ln of x plus h minus ln of x over h. And that's the derivative formula for just about figuring out anything. You can actually spend a lot of time and derive almost all of them using this structure. But you have to remember some of the rules of log and rules of ln. Ln is simply the natural log. Ln is log base e of whatever value here. And if you've got to look back, if I have log base 5 of 25, what it's asking is, what do I have to put 5? What exponent do I have to put here to equal 25? Well, it's clear that 5 to the 2 is 25, so the answer in your calculator for this would be equal to 2. Well, ln is just to the base e. That's all ln is saying, what do I have to put e to get whatever's here? So remember all your log rules. And one of the log rules says that when I have a log or a ln that is ln x minus log y, I can rephrase it as log x divided by y. I can take whatever numbers are in there, divide them, then take the log. Very handy, remember. Well, I have that situation here. I can rewrite that as ln of x plus h over x, which is this term divided by this term because I have two logs or lns subtracting each other. All of it over h. Okay, well, that's a good step. And don't forget, we're looking for the limit as h reaches 0. Also notice this fraction, that any fraction, when I have 2 plus 4 over 6, I can rewrite it as 2 over 6 plus 4 over 6. Now it's clear up here that this is 6 over 6, it's 1. But down here it's 1/3 plus 2/3, and it's also 1. So you can divide any fraction so long as you use the common base. Well, this I'm going to rewrite. This I'm going to rewrite as x over x plus h over x. And it's clear that x over x is 1. So that means I can rewrite this entire fraction as 1 plus h over x. You might get a feeling that e is going to come into play here, and it is. So that means I'm going to rewrite this whole thing as the limit of ln of 1 plus x, 1 plus h over x, over h as h approaches 0. Well, I can also remember that anything like this, 5 over 2, is the same as 1 over 2 times 5. You're just taking this part out, putting it in front as a multiplier. Well, I'm going to do that with this h. I'm going to rewrite this whole thing as 1 over h as a multiplier. So I'm going to take this part in front, and I'm going to just multiply the ln of 1 plus h over x. It's the exact same thing. And don't forget, it's all to the limit as h approaches 0. So that means I have this now. Well, here's another feature of lns. If I have, or logs, if I have 5 log of whatever, 6, or x, I'm allowed to put that 5 over here as an exponent. I'm also allowed to take the exponent and put it back in front as a multiplier. That's the nature of logs. And you can test this out. If you take the log of, I don't know, it doesn't matter, 100, which is supposed to be 2, and you square it, you'll discover that 2 times that also works. It doesn't matter how you go about it. Just remember that this is one of the features. Now, let me go back to here and say I have a multiplier in front, but instead I'm going to put it over here as an exponent. So I'm going to get rid of it. And this ln 1 plus h over x, I'm going to now put it as an exponent of 1 over h. Well, we're very close here. We just now have to say, I don't like this h over x. I'm going to replace this with the letter u, and I'm going to make u equal to h over x. Just remember that we were looking as h approaches 0. What happens to this fraction as h approaches 0? It's clear that this fraction also approaches 0 or becomes 0. So that means, in this case, if we're going to replace h with u, u also is approaching 0. So that means if we're going to replace it, we can now say, well, we're going to replace all of my h's with u, but u is also approaching 0 because I can see its relationship here. Well, that's good. Let's just take this h over x and we're going to replace it with u. That makes my life a little easier. And what about this 1 over h here? I don't have a good replacement for it. I have u is equal to h over x. How do I get 1 over h is equal to something from this? Well, first thing you have to do is you have to multiply 1 over h on both sides. They cancel out here. So you're left with 1 over x u over h. Well, now I just want this to be gone because I want 1 over h here. Well, I multiply it by 1 over u on both sides. Great. It's going to cancel here, and I'm left with 1 over h is equal to 1 over x times 1 over u, which could also be rewritten as this. But actually, keep in mind this separation for a second. So that means this 1 over h is replaced with 1 over x times u. The only problem with that, we're kind of close to something that might look like e, but there's an x in there. Well, keep in mind I can replace this fraction as these two separate fractions multiplying each other. I can replace 1 over u times x as 1 over u times 1 over x. The other rule of exponents is that if I have 5 to the 2 or 5 to the 6, I'm allowed to rewrite that as 5 to the 2 to the power 3. And the exponent of an exponent multiplies to get where I want. Well, here's my multiplier. I'm going to sort of split it up. I'm going to now say I'm looking for the limit as u approaches 0 of ln 1 plus u to the power of 1 over u. And that's to the power of 1 over x, because these will multiply and come up with that and become eventually 1 over ux. But I want to separate it for one obvious reason. I want to take that 1 over x, that's an exponent, and use my log rule and put it in front. And it doesn't have to stay in the limit because there's no u in it, so it's just a constant now in front. So you can see where we're going now. And we're now left with this thing in here that looks a lot like e. It looks a lot like this. And which one does it look like? It looks like the one that's approaching 0, and which is n, or 1 over n, or in this case u, and 1 over u as u approaches 0. So we can see this part here becomes e. As we approach 0, we get ln of e. Well, as I said, ln is to the base e. It's essentially log to the base e. And e is here. So essentially we're asking, what do I have to put to the power of e to equal e? That's what this asks. What do I have to put to the power here to equal this? It's clear it's a 1. So the answer to this, ln of e, is always 1. So that entire thing simplifies to 1 over x, and once we reach the limit, it's times 1, which is 1 over x, which means when f of x is equal to ln of x, the derivative of f of x is 1 over x. It looked like a hard way to prove it, but it's actually not. It's just about showing that we can remove 1 of x out of it, 1 over x out of it, and prove that we're finding the ln of e. Once you can solve this or prove this, the rest become pretty easy. Now let me explain how it comes pretty easy. By explaining something that's called implicit differentiation. When I have something like this, I have normally, this is a circle, and I can rearrange this and say, well, if I rearrange this for y, I get 9 minus x squared, and it's the square root, and when I take the square root, I ended up with plus or minus. If you don't see how I got that, it's y squared is equal to 9 minus x squared. To get rid of this, I have to take a square root on both sides. But when I take the square root on both sides, it creates this plus minus situation. That's simply because minus 3 squared can be equal to 9, and 3 squared can be equal to 9, and I have to account for it with this plus minus. So now I have y expressed like this. If I want to take the derivative of this based on changes to x, I should actually convert it to a fraction so that I can do the chain rule and keep that plus and minus here. The chain rule says I bring the half out front, so I bring the half out front, plus or minus. I keep the 9 minus x squared as it is, and I lower this half by 1, so it becomes negative a half. The chain rule also says I have to take the derivative of the interior. Well, 9 is just 0, and minus x squared becomes minus 2x. So that's the derivative of the interior, minus 2x. So far, so good. When I look at this, this minus 2x multiplies over to here, and it becomes minus 2x over 2. It's clear the 2's cancel, and I've got minus x in front times this bracket, which is to the power of minus a half. Well, that's the same as plus or minus, and you don't need the minus x anymore because the plus or minus accounts for both a minus x and a plus x. And this negative half essentially just sends the whole thing, 9 minus x squared, to the half. It sends it all to the denominator. That's what the minus does. Minus a half simply sends it to the denominator as a half. That could also be rewritten as plus or minus x over square root 9 minus x squared. That's exactly what the half means. It means it's the square root. So this is the derivative of that, or this is as well. They're both the same thing. Let's instead look at implicit differentiation, which means I'm going to leave it like this, and I'm going to take the derivative of y based on changes of x. But it's clear I can't see how y is changing based on x. So what I must do is sort of the chain rule. I must take the derivative of y based on y, and then multiply it by the derivative of y based on changes to x. So this little thing stays here. There's not much I can do about it. But the derivative of y here, based on y, is the same as you would do for x squared. It's 2x. And for y squared, it's 2y. Follows the same rules. Just you do it with the y. So looking back at this, if I take the derivative of this, I get 2y. But I must multiply it by the derivative of y based on changes of x, which I don't really know yet. Now, if I take the derivative of x squared based on x, I get 2x. If I take the derivative of 9, I get 0. And I'm left with this. Now, the secret is you're trying to get this term all alone equals something, because this is the derivative. This is the derivative of y. You can never really solve that. That's the left side of the equation. You're always solving the right side. Well, my first step, this is being added to it. I'm going to send it to the other side. So I get this is equal to minus 2x. Now this thing that I'm trying to isolate is being multiplied by 2y, so I'm going to multiply both sides by the reciprocal so that it cancels out. When I multiply this side by the reciprocal, I get that. Okay, fair enough. So far, the the derivative is equal to that. It's clear the 2's are going to cancel out, and I get that. Well, that's not what I solved when I did the derivative, except that I have y here, and I have y is equal to something up here, which means I can replace this y with the equivalent. That's a rule of mathematics. Since I was taking it based on y anyway, and I have a definition of y, I can replace all of y with that. This minus up top divided by plus minus essentially just becomes a plus minus up top. So I am ending up with, after I replace y, with plus or minus x over square root of 9 minus x squared, which was the same as the derivative we figured out before. This will work. You can leave line equations in this format. It's clear that the only thing you're going to be left with here is plus 2, but my point is you can derive the y and try to just your whole goal will be to isolate the dy over dx aspect. Makes life a lot easier, and here's why. If I have y is equal to e to the x, that's very hard for me to derive. But I can find its reciprocal. I can find its reciprocal. That's just swapping my x and my y's and solving for y. Well, I can't solve for y as an exponent. The only thing I can do is take a ln of both sides in order to get that exponent down. That's how you deal with exponents. Now I can follow the ln rule. This to the exponent of y is the same as y multiplying ln of e. Well, ln of e, as I've already expressed, ln is the natural log based on e. And when you ask this, you're saying, what do I put to the exponent of this to equal that? Well, it's clear the answer is always 1. So ln e is always 1. So I'm left with this. This is clearly the derivative of this. Makes a lot of sense. Oh, sorry, the reciprocal. Now, you might say, what does that have to do with the derivative, man? All you've done is tell me the reciprocal, right? Now, the good news is I know what the derivative of the reciprocal is. The derivative of the reciprocal is y prime is 1 over x, because we figured it out already. How am I going to go, why would we go over here? It doesn't do me any good. Well, this is the reciprocal of that, right? So that would stand to reason that the reciprocal of this is that. So let's just start by switching the x and the y. I'm going to start by switching the x and the y. That's what you do when you want to find a reciprocal. You might be saying, why? We already know the reciprocal's right up here. Yeah, okay, fair enough. But we're going to stop right here, and we're going to use implicit derivation to solve this. X is equal to ln y. And that says I'm taking this side based on dx, the derivative of this, and I'm taking this based first on dy, and then I've got to multiply it by dy dx. Okay, let's do that. What's the derivative of x over here? It's clearly 1. What's the derivative of ln y? Well, first you take the derivative based on y. We know that the derivative of ln x is 1 over x, so that means the derivative of ln y is 1 over y. And it's got to, though, we then got to include this term. And this is the term I'm trying to get all alone. Now you might say, well, you're finding the derivative of this thing here, but remember, we made this the reciprocal, which is identical to that. The reciprocal of ln x is the identical thing to e to the x. We just did the derivative while it's in ln x format. Okay, how do I get this all alone? It's being multiplied by 1 over y. I have to multiply it by y over 1 on both sides. This is 1, so it's clearly it's just going to be y over 1 on this side, which is the same as y. So this cancels out, and I'm left with the derivative. The derivative of x is equal to ln y, which, by the way, is the exact same equation as this, is y. Well, that's no good, except that, remember, just as we did for the x squared plus y squared equals 9, we can now replace y with what we know y to be equal to. Y is equal to e to the x. So that means the derivative of this is e to the x. And keep in mind, we started with the derivative in this format, which is a lot easier for us to solve than in this format. This is actually very clear that the derivative ends up being y, and that y is equal to e to the x. That, to me, you might say, well, you just did roundabout. You cheated the whole way. I didn't. I did implicit differentiation, and it works the same way as it did for the circle. And it'll work no matter what. Okay, let's see if you can do it for y is equal to 2 to the x. Now this has a couple tricks to it. This is very hard to do. They do all sorts of trickery. They do e to the ln of 2 to get to 2, which is just annoying. Instead, I'm going to find the derivative, or sorry, the reciprocal. Let's start by switching the x and the y's. We need to take a ln of both sides. Ln 2 to the y. We can now bring the y down, and we get y is equal to multiply ln 2 is equal to ln x. Well, to get rid of this ln 2, which is just a number, I'm going to divide both sides or multiply both sides by the reciprocal, and I'm left with this. Y as the reciprocal to this one here, the reciprocal of 1, y is equal to ln x over ln 2. Well, this you're going to have to go back to your knowledge of how to use your calculator. Ln x over ln 2 is the same as log base 2 x. And to prove that, use any number here, like use log base 2 of 5. And since your calculator might not have log base 2, use log base 10 of 5. And then over here find log of 5 and log of 10. Now that's a little bit too easy, but it'll still work. Oh, actually ln of 10 and ln of 5 will still work. Let's try that actually. Let's take ln base 10 of 5. So I'm going to just write it up here. Log base 10 of 5. And we're going to see if it's the same as ln of 5 divided by ln of 10. Okay, I don't have to do the base 10 because all logs are just base 10. I just got to click on log and I get 0.6989. Then I'm going to take the ln of 5 and I'm going to divide it by the ln of 10. And I'm going to click my equals and I get the same number. So this is a universal rule. Ln of something divided by something else is the same as log base of whatever that is. Looking for that. So that means this here is the same as log base 2 of x. So the reciprocal of this exponent here is y is equal to log base 2 of x. Easy to prove, easy to go through. Now, it's clear that the reciprocal of this will be that. So I'm just going to start by switching the x and the y's like this. This y I'm going to switch to an x. This is now going to be the reciprocal. And the reciprocal is obviously the same as the equation at the top, right? But now I must solve for y. Okay, well, how do I solve for y? This is a little bit backwards. We got to go backwards and realize that that is the same as ln y divided by ln 2. It's the same rule. I'm just going backwards. Fair enough. I'm going to replace it with ln y is equal to ln 2. And then I'm going to get rid of the ln 2 and multiply it over here. Like that. So this is still the reciprocal. If in doubt, you can take Desmos, and it's really interesting, and you can say, okay, Desmos, if I take y is equal to y is equal to 2 to the x, is it going to be the same as ln 2 times x is equal to ln y? Let's hang on, let me make sure I got it, the same information. Is it going to be ln 2 times x is equal to ln y? Well, it's just a moment. It doesn't like having the x in front like that. There we go. Yes, it is. Yeah, it does a weird thing because it's taking the ln of 2x instead of x as a multiplier. Yes, it does. It is the same. If I'm going to write it this way, I've got to do it multiplied by bracket x. So that oh, no, it still doesn't accept it. It considers it a ln. So I've got to do x times that. So it is the same. And if you wanted to see if it was the same as when I had it, which is ln y divided by ln 2, it will be the same. So it's clear that the reciprocal in this format is the same item. Okay, we've established that. Now let's take the derivative on both sides. This is just a number. Ln 2 is just a number. If you punch it into your calculator, you're always just going to get a number. And that's the number. We could use the decimal, but this is much more accurate. The derivative of x here, based on x, is 1. So I'm left with ln 2 is equal to, times 1, is equal to, what's the derivative of this? Well, we've already established the derivative of this based on y is 1 over y. However, we must now multiply it by dy over dx. And this is the part we have to isolate right here. Well, to get rid of that y, I have to multiply by y over 1 on both sides. Y over 1 on both sides. It cancels on the right side, and I have what appears to be the derivative of that funny little reciprocal. I have that dy over dx is equal to y times ln of 2, which doesn't make sense until I realize I have the definition of y right up here. And I've essentially proven, using the reciprocal and using my knowledge of what the derivative of ln x is, that ln x's derivative is 1 over x, this is much easier for me to prove than to prove that. And it works with any exponent. The only thing I can't really get into with this is an explanation of how if it's 2 to the x plus x squared plus 3x, in this case you have to take the derivative of what's up there. There's a whole bunch of rules. You have to take ln 2 times the actual thing, so plus 3x, and I believe you have to take the derivative as that as well, but we'll get more into that. Since proofs are usually the base object, that's the best way to go. And you can even prove something like a log 1 instead. That's difficult, like well, 10 to the x is very easy to prove. The derivative of, or the reciprocal of that is 1 is equal to log x. If I go back and take the reciprocal backwards, I get that. When I take the derivative of both sides, I have to convert this to ln. That's the same as ln y over ln of 10. Okay, that's the same as log, because you want it in terms of ln. Then I can multiply this side, both sides, by ln 10. Then I've got to take the derivative of both, so that's 1, and I'm just left with ln 10 is equal to 1 over y times dy dx. I multiply both sides by y, and I'm left with dy over dx is equal to 10, ln 10, times y. But then I remember y over here is 10 over x, 10 to the power of x. So it's kind of easy to show the derivative when you understand implicit differentiation, and it's useful. I'm going to stop there. And I think we've done it all, right? We proved that the reciprocal of e to the x was y. Did we proved that already, didn't we? Oh no. I can't remember. Oh yeah, we did prove that. We showed that it ended up being dy dx is equal to y, and then we just substituted the y. Some might say this doesn't seem legit, but it works. Implicit differentiation works for standard equations, so there's nothing wrong with doing it here as well. I just find it's a little more clear to see how you get there than the other methods. You can go look up other methods on YouTube, but they all kind of cheat